Hello, everyone. For this project, each engineering consulting team was hired by the Environmental Protection Department of the Government of the Hong Kong Special Administrative Region and were given the task of designing a smog tower that would be most effective in removing smog particles from the air, as well as any other improvements that the team felt would improve efficiency and effectiveness. The smog tower was modeled to be in Hong Kong in an attempt to improve the concerningly bad air quality. While the model of the smog tower did show an improved air quality in Hong Kong, there is still area for improvement in terms of physical design, efficiency, and effectiveness. The goal of this project was to determine how to implement an electrostatic precipitator to meet whose air quality specifications. As you can see, the team outlined the three main customer needs described by Hong Kong's Environmental Protection Department. The first being that the team's proposed smog tower should optimize energy production while also minimizing costs. The team set a maximum spending cost of $10,000 and determined that the design would result in a cost of $8,500 for energy production, thus meeting their technical requirement. The second design specification pertained to the size of the physical design model. The team set the technical requirement for this specification to be that the base area of the structure was no more than 600 meters squared. The final dimensions of the team's smog tower designed was 424.92 meters squared, which met the specification. The last specification was to have a model that would result in high reports of air quality. The team determined that to design the model for improved smog towers should be able to capture 95% of PM10 and 50% of PM2.5 particles in the air. The team was successful in meeting these specifications, seeing that the design model captured 99% of PM10 particles, but fell under the specification by only capturing 32% of PM2.5 particles. While this efficiency could have been increased, it would have come at the expense of making a much larger system that would also cost a significant amount more to build. As you can see under the physical model, this key equation shows the equation of a motion for a particle, and the image underneath shows the direction of the different forces acting on the particle. As you can see from this equation, you calculate the motion of the particle by adding the gravitational force and the upward drag force together, and then subtracting the electric field force due to other charges from that quantity. This governing equation allowed for a particle to be modeled inside the system and determine what factors are significant to optimize.
There were numerous critical parameters to consider while generating a MATLAB simulation to model a system aimed at removing PM10 and PM2.5 particulate from the atmosphere in an attempt to clean the air of Hong Kong to a level deemed appropriate by the World Health Organization's air quality standards. Among these parameters, the most significant factors of the MATLAB simulation were identified to be the overall geometry of the structure for the system, the potential difference between the plates comprising the electrostatic precipitators, the distance between the plates comprising the electrostatic precipitators, and the wind speed of the region surrounding the system. It is important to generate the model about the overall geometry of the structure for the system, as there are size constraints for what would be considered feasible to implement. With this concept in mind, a circular base for the structure is the optimal geometry compared to a rectangular base because a particle is able to travel through the structure in any direction and still be collected by the electrostatic precipitators while eliminating the occupation of any unnecessary space. As a result, the structure allows the system to be flexible in regard to the locations it can be implemented in Hong Kong, which is a region that already experiences problems with the amount of space it has. In addition, it is important to generate the model about the potential difference between the plates comprising the electrostatic precipitators, as there are efficiency metrics and cost constraints for what would be considered feasible to implement. With this concept in mind, the potential difference must be enough to allow the system to function properly and collect the PM10 and PM2.5 particles from the air in an efficient manner while not exceeding the point at which the cost makes the system not feasible.
Other key significant factors were considered, and these factors had large-scale impacts on the overall design of the electrostatic precipitator, including the distance between the plates and the wind speed. On initial thought, one may think that as the number of plates in the electrostatic precipitator or smog-free tower increases, the cost would also increase. However, the system is not quite that simple. The smog-free tower requires energy and power to function. The distance between the plates is dependent on the electric field desired. In order for the system to output the same efficiencies and results, as the distance between plates decreases, the voltage and thus the amount of power decreased, even though more plates were being used. Simply put, lowering the voltage is much more significant as a cost-reducing measure than the number of plates is. These findings are depicted on the graph to the left that shows this linear relationship. One key thing to note is that it's not practical to make the distance between plates infinitesimally small. Factors such as maintenance and installation must be considered. So for the model that was created for the Hong Kong government, the distance between plates was selected to be 0.14 meters or 14 centimeters, the same distance that Rusegard used in his smog-free tower that was analyzed as a case study. Another noteworthy factor to consider was the wind speed. As the winds increase, the speed at which the PM particle travels also increases. This means that for a given particle, it's possible for the wind to blow it so fast that the particle blows straight through the tower and is never collected. Since a tower specific to Hong Kong is desired, the typical max wind speeds were found in Hong Kong to be approximately 5 meters per second, or 11.2 miles per hour. Since this is the typical wind speed in Hong Kong, it's important that the design system works in Hong Kong. In order for the PM particle to get caught in the system with the electric field set, the tower needs to be 25 meters long. This comes as quite a surprise, as the case study that was analyzed from Studio Rusegard depicted a taller and much skinnier tower. This was because their tower assumed a controlled wind speed of 1 meter per second, where according to the design MATLAB model, this means that their tower would have been 2 meters wide, in fact, much smaller than our model of 25 meters. In order for it to be effective in Hong Kong, the electrostatic precipitator, or smog-free tower, must look less like a tower and more like a building. The graph on the right depicts the linear relationship between tower length and wind speed. It's important to get a feel for this MATLAB model. It takes in key constants that play into the governing equations, and then it uses Euler's method and using a given set of initial conditions to loop through the governing equation from Newton's second law to either print out position or velocity in terms of time. Here's an example execution where it analyzes PM10 particles and then outputs the graph of x versus y. It outputs a nice graph and shows you all the desired information, as well as outputting text to the user, including the cost per day, and the amount of particles filtered.
The system generated according to the MATLAB simulation meets most of the engineering specifications indicated in the chart of the design goals section of this poster, and is capable of removing 100% of the PM10 particles from the air, as well as 32% of the PM2.5 particles from the air. These efficiency values mean that the system will be able to remove approximately 853,114 PM10 particles and 298,503 PM2.5 particles from the air every day, which is equivalent to approximately 311,386,610 PM10 particles and 108,953,595 PM2.5 particles being removed from the air every year in Hong Kong, which is instrumental in allowing the region to meet the air quality specifications set by the World Health Organization. The efficiency of the system is depicted in the figures of the effectiveness section of this poster, which plot the vertical position of a particle in an electrostatic precipitator against the horizontal position of a particle in an electrostatic precipitator. As demonstrated by the plot titled PM10 Analysis, a PM10 particle is able to travel through an electrostatic precipitator beginning at any initial vertical displacement and still be captured by the system. However, as demonstrated by the plot titled PM2.5 Analysis, a PM2.5 particle must travel through an electrostatic precipitator beginning at a maximum initial vertical displacement that is 32% of the distance between the plates in order to still be captured by the system. Overall, the system, as generated by the MATLAB simulation, is very effective in removing these particles from the air and will definitely contribute to Hong Kong's attempt to reduce the pollution levels in order to meet the appropriate specifications relating to the air quality in the region.
And now for the ideal site choice for this model. Obviously, the ideal site choice for this model would be anywhere near a source of this type of particulate matter pollution that produces these PM10 particles and masses. Such places would include roads and/or marinas due to the emission from the vehicles, industrial activities like construction and/or mining, in any place or factory that produces energy, whether it be residential or industrial. For future considerations relating back to the site choice, something to consider would be the permanence of the constant production of these particles. Having the option to place the system near a road, where for the foreseeable future will constantly be producing large amounts of these particles, or near construction, where it will eventually be completed and will no longer produce these particles in masses like before. The resources to implement and run the system, which costs millions of dollars, will be put to better use if placed in an area that has a constant PM10 particle output, like roads and marinas, as it will be more efficient to serve its purpose. Other things to consider would be making sure there is adequate space to implement the system, as it is large enough to require adequate planning beforehand for a construction team. The cost per electrostatic participator of the structure, as it is expensive to implement for only one, relating to concerns with the large-scale implementation of this technology, as it would cost millions of dollars to implement multiple of these structures around a city and or country, which will basically require a lot of planning beforehand. And finally, the sustainability and the maintenance. These structures will require maintenance and will have some sustainability issues concerning the technology. This type of electrostatic participator uses positive ionization, which produces an output of ozone, which in large amounts can be harmful to the environment and to breathe. So for long-term usage, this may be considered when used in large amounts. Overall, this is a feasible system, and the model is practical, but the high costs and the size of each individual system is something that gets in the way of its practicality. The original model of the system, developed by Rosengard, was not implemented to its fullest extent, and being an artist, he could have indirectly prioritized its looks and aesthetic rather than consider the technology and the cost itself of the system. The total size ended up being 425 meters squared, and the cost ended up being $3,100,000.